Hello, in this video we studied triple integrals and how to use triple integrals to find the volume of some solid region and how to find center of mass, moments of inertia of a solid region. Before we move to detail, I would like to give you some picture how to move from single integrals to double integrals and from double integrals to triple integrals, okay? Suppose that you have some function y equal to f of x, and suppose that this function is greater than or equal to 0, you need to find the area of this region. That is the area problem in calculus 1. So the area of this region is nothing but definite integral from a to b f of x dx, right? I have integral from a to b, dx is outside, makes sense? So I fix some x in here, you see? Y will go from where? From 0 to f of x. So I can write 0 to f of x. And then here I have dy, right? Or we can write in general the whole r in here and then dA. Make sense? That's how we move from single to double. Okay? And now if you have some function of two variables, z equal to f of x and y, this function describes some surface in R3. And we also learn how to use double integral to find the volume of the solid region, right? Bounded by the surface. And suppose that, this is greater than or equal to 0. So make sure that the surface is above the axis. And in this situation, the volume is equal to double integral over r f of x and y and then dA. Look at this. What is the difference between this guy and this guy? The difference is in the function, right? Makes sense? Here you have 1. Don't forget that. Okay? And by the logic of this picture, I might think, yes, maybe I can move this function, that is z equal to f of x and y, right? Move to integration limit of a triple integral. Make sense? So you may think like this. This is the picture, right? This is z. If you consider some point in here, there should be x, y, and z. Agree? X and y and z. So I may find the volume of this solid region by the following formula. That may be triple integral, but from here we'll discuss in detail later, right? I just want to talk about this. When you fix some x and y right here, you can see actually z will go from where to where? Z will go from 0, right, to this point, to f of x and y. Makes sense? So basically, you can write this is from 0, f of x and y, and then dz right here, and then dA. Okay? We'll discuss about that later, okay? But by doing so, we can determine the triple integral. Make sense? Look at this. Again, right? From the area problem, you write in the form of iterated integrals. And if you have function f right here, you have volume. So you may write in the double integral form like this. Agree? And by doing so, if you have some function right here, right? Some function right here. Let's say function of 3 variables, right? G of x, y, and z. You may consider triple integrals of this function over the solid region in R3. Not in R2, right? Not in x or y plane. Double integrals are taken over some planar region, right? But triple integrals are taken over some solid region in R3. Make sense? The first example, we want to evaluate the following integral from 0 to 2, from 0 to x, and here 0 to x plus y. We have ex, y plus 2z, dz, dy, dx. Look at this. dz, right? And then dy, dx. I write here dz, dA, right? And dA in this example is written in the order dy, dx. Make sense? So, you know, in this order, we have to integrate with respect to the z first. And then what you get, you integrate that function with respect to the y, right? And finally, you integrate with respect to the x. And each time when you integrate with respect to the z, you look at x and y as constants. Make sense? All right, let's solve this integral. First, I have to find the inside, the very inside integral with respect to the z, right? So here we have exy and only 2z right here. That integral is equal to, I write here from 0 to 2 because we don't change that. We have exy. I put one z in here because that is constant, you know, antiderivative or constant, just add the z, okay? The second one is ex. The antiderivative of 2z is z squared, right? So I have ex z squared. This is evaluated from 0 to x plus y, dy dx, okay? And then you plug x plus y and 0 in the position of z. You get the following one: 0 to 2, 0 to x, ex y x plus y plus e to the x, and then x plus y squared. The function equal to 0 as 0. So now you have dy dx. That is already iterated integral, right? Double integral. And you are free to find this. Makes sense? And now you integrate with respect to the y. So we have the following one: 0 to ex y xy, right? So if I open the parenthesis, I will get the following one: ex x y squared over 2. That is antiderivative of y right here. So I multiply y with the y, I get y squared, right? Then I have ex y cubed over 3. All right, next, ex plus y. I can use, you know, the power rule. So I write that is ex x plus y cubed over 3. This is evaluated from 0 to the x, and finally I get the x. All right, now I plug x and 0 into the function. I get integral from 0 to 2. The first term gives me e to the x, x cubed over 2, plus e to the x, x cubed over 3, plus e to the x, 2x cubed over 3, right? And then you plug 0 into this function, you get the first two terms gives me 0, the last term gives me ex, and then x cubed over 3 dx. So you might simplify. For example, this term and this term will be cancelled out. You have this term with this term only, right? So if you take ex out, you get, let's say, ex x cubed, right? You have 1 over 2 plus 8 over 3 right here. So basically this is equal to 3 plus 16 over 6, right? So you have 19 over 6. Basically this is equal to 19 over 6 integral from 0 to 2 x cubed ex dx. This is very special integral, right? The general form looks like this. So for such integrals, we need to do integration by part, okay? So I'll do the following one. I put u equal to x cubed, and then dv equal to ex dx. From here I get du is 3x squared dx, and then v is ex. By the formula of integration by part, our integral is equal to u times v, right? Subtract the integral of v du. Okay, with subtraction right here. So the integral equal to 19/6 x cubed e to the x evaluated from 0 to 2, okay, minus 3x squared ex dx from 0 to 2. We still have this form, so you have to do integration by part until, you know, this term disappears. Make sense? So I have the following one. Let's say this part, right? I put u equal to x squared, and then dv equal to ex dx. I have du equal to 2x dx, and then v equal to ex. Then the integral from 0 to 2 x squared e to the x dx equal to x squared ex evaluated from 0 to 2 minus 2 times x ex dx from 0 to 2. So you need to do one more time, right, to find this integral. Alright, so I put u equal to x again, dv is ex. I have du equal to dx, v is ex. Alright, and the integral from 0 to 2 x ex dx equal to x ex from 0 to 2 minus ex dx from 0 to 2. So we are done because this integral is just ex, right? Evaluated from 0 to 2. I have x ex from 0 to 2. Alright, now let's be careful to compile everything, right? First, you have this term times 2 right here, right? And then subtract, okay? This integral right here is x squared ex. That's what you have in here. Makes sense? And then you have to plug this into this formula. Agree? So overall, I will have the following one. I have 19/6 ex cubed ex. Okay, here from 0 to 2. So plus, not plus, minus 3 minus 3, okay, all this. Makes sense? Alright, so if we rewrite that, we have the following one. 19/6 x cubed ex minus 3 x squared ex. 3 with negative 2 is plus 6 x ex, and then negative 3 with negative 2 is 6, and then with the negative I have minus 6 ex, everything evaluated from 0 to 2. Makes sense? And the last step is just plug 2 and 0 into this function, so you get 19/6. At 0 I get, at 2 let's say, I have e to e squared, right? And the inside I might have 2 cubed minus 3, 2 squared plus 6 times 2 minus 6, because I already take e squared out, minus at 0 this term is 0, this term is 0, this term is 0. At 0 I have just, plus 6 e to 0, which is 1, right? So overall I get 19/6 e squared over 3, and then plus 1, which is approximately equal to 65.797. You see, it's not easy at all, right? So basically we need to do, different techniques in here, and this example is very good because, it reminds us about this integral, and we need to use integration by part. In the following example, we will use triple integral to find volume of ellipsoid given by 4x squared plus 4y squared plus z squared equal to 16. Of course, we can use double integral to do this. Make sense? But now we want to write a triple integral that gives us the volume of this solid region. So, you have some ellipsoids right here, okay? And here you might have something like this. So, forgive me about that, but I hope you can imagine we have some ellipsoid in here, okay? So, actually this ellipsoid is symmetric with respect to the origin, right? So, if you look at this, right? So, this ellipsoid has 1, 2, 3, 4, 5, 6, 7, 8 parts. How? For example, if you just consider the first corner right here, right? The first corner right here, so you have 1, 8, and then above the xy plane, and you have the symmetric part, which is under xy plane. So you have 4 corners in here. So that means, you have 8 parts, right? So basically, in order to find the volume of this ellipsoid, I just need to find the volume of the part in the first corner, which is above the x-axis. Make sense? Which is above the x-axis in the first corner. Agree? So I say, yeah, that is equal to a times integral over v1, okay, dv, where v1 is the part of the ellipsoid with respect to the first corner and above x-axis. Make sense? The first corner. So if you make the region, you will have the following one. Yeah, this is the first corner for you. Agree? That is the region. Alright, so how to rewrite this integral as an iterated integral? Look at this picture again, right? So now you consider just the first region right here. So let me erase a little bit. And even I can erase this. I make another picture. So this is my, the first corner. And z is something in here, okay? Makes sense? If you pick some point x and y in here, so you would have some corresponding z right here, okay, which is f of x and y. And as we discussed at the beginning of this video, you would think, yes, this triple integral is nothing but integral from 8, I write in here over r, okay, and here I have integral from 0 to the z, makes sense, and then d z right here, and then dA, okay. Let me write that very naively, okay. So we need to work on this and on this too. Makes sense? Alright, so I would think, yeah, our solid region looks like this. We have to describe this solid region. First one, if z is equal to 0, we need to find the region on xy plane. So the region on xy plane looks like 4x squared plus 4y squared equal to 16, which is x squared plus y squared equal to 4. That is the circle, right? And then the z is between 0 and 16 minus 4x squared minus 4y squared square root. Is it correct? Because any point in this solid region, is under the surface. So that means any z which is less than or equal to the function value. Makes sense? So, from the equation right here, if you want to write the function z, you may think, yeah, that is z squared equal to 16 minus 4x squared minus 4y squared. And you get z equal to square root of everything in here. We don't have minus because we consider the first corner, right, which is above the xy plane. Make sense? So I may have the following interval of g of z. So basically we already have right here. Instead of z, I can write that is square root of 16 minus 4x squared minus 4y squared. Agree? And now, if you want to rewrite this, right, in terms of dx dy or dy dx, that is your choice. But again, we apply the technique we learned for double integrals. Make sense? Okay, so let me copy this formula. Okay, and I write in here, that is 8. I want to integrate with respect to the z, and then maybe I want to write in the order dy dx. Okay, so I have 3 integrals in here. Dx is the outside. We know x goes from where to where? From 0 to 2, because our circle has radius equal to 2, right? So I have from 0 to 2. And now for y, if I fix x right here, y will go from 0 to this point, right? So that means I have to solve the equation of the circle with respect to the y. Makes sense? For this, I can see, yeah, actually y is equal to 4 minus x squared and then square root, because y is bigger than 0. Makes sense? So I have the following one. From 0 to square root of 4 minus x squared. And then for the z, I have 0 in here. And then this is square root of 16 minus x squared minus 4y squared. Okay? So we have to integrate with respect to the z first. That is 8 integral from 0 to 2, from 0 to 4 minus x squared, and here I have square root of 16 minus 4x squared minus 4y squared dy dx. Look at this. This integral is nothing but 8 times, right, 0 to 2, 0 to square root of 4 minus x squared, f of x and y, dy dx. You see that? Where this is the z. So, as we discussed how to go from single to double, from double to triple, we just shift the function, right, to the integration limit right here. Oh, right here. Right here. That's it. Now, our job is to evaluate this double integral. Alright, so let's find this integral. Look at the region, right? The region is, 1/4 of the circle. So this region is very good for polar coordinate. Let me describe this region using polar coordinate before we integrate this. So this is nothing but r is between 0 and then 2. Theta is between 0 and pi over 4, right? And we have x equal to r cosine of theta, y equal to r sine of theta, and x squared plus y squared is just equal to r squared. Okay? Then our integral star right here looks like 8 times. You may choose integrate with respect to the r first and then with respect to theta, right? That's your choice. Or you want to do theta first and then r. But I write dr d theta. So theta goes from 0 to pi over 2. R goes from 0 to 2. The function, according to this, 16 minus 4x squared minus 4y squared is just, 16 minus 4r squared, right? So I have square root of 16 minus 4r squared, and don't forget we have r in here. Okay, then in this you can see, yeah, this integral does not depend on theta, right? So this integral is product of two integrals from 0 to pi over 2 d theta times integral from 0 to 2 r square root of 16 minus 4r squared dr. Make sense? The first integral is equal to pi over 2, which is good, times a. For the second integral, I have to put u equal to 16 minus 4r squared, right? And from here I get du is negative 8r dr. So r dr is equal to du negative over 8. Okay, because we have r dr right here. We do substitution. And if you want, you can change integration limits right away. When r equal to 0, u equal to 16. When r equal to 2, u equal to 0, right? So the second integral is equal to integral from where? From 16 to 0, right? You need to keep the order right here because, you know, r0 corresponds to 16. R dr is negative du over 8, and we have square root of u, right? So I will have this equal to negative 1/8 u 3 over 2 over 3 over 2 evaluated from 16 to 0. Make sense? So you plug 16 and 0 into this function. At 0 the function is 0. At 16 you have minus negative, right? So I have plus. So I have 2 over 8 times 3 right here, and then 16 3 over 2. Makes sense? If we simplify this, I would get 2 times 4 cubed over 3 times 8, right? So we have 16 over 3, I guess. All right, so we compiled 16 over 3 and 8 times pi over 2, which is 4 pi, right? So basically I have 4 pi times 16 over 3, which is 64 pi over 3. Okay, so that is the volume of our solid region. In the textbook, they give you another method, right? They don't use polar coordinate, but you know, in this situation, our region R is very good, which is very good for polar coordinate, right? We learned this, you know, in the previous video. Make sense? Okay, let's go over this problem again, right? We need to find the volume of this ellipsoid. So they ask us to write double integral. Here it is, right? So for this, we know, yeah, we can rewrite in this form. So we need to determine the integration limit of z. But how do that? We can do that using the equation of the surface, right? So the equation of the surface, look at this picture. For each point right here, so you have to integrate, right, with respect to the z. You see that? So z will go from this level to this level, right? Which is f of x and y. Makes sense? You know, this technique is very similar to the case when you consider double integral right here. So if you fix some point, right, in here, you find the level, the interval of z. In here, if you fix some point right here, you find the interval of y. That's it. You know, this is a very similar idea. So I hope that you will not have any trouble, right, to evaluate a triple integral or to rewrite a triple integral in the form of iterated integrals. Right? In order to finish this video, let's have one more example. Learn how to determine the limits of integration. That is always important. Okay, so they ask us to set up a triple integral for the volume of the region in the first octant bounded by the cylinder z equal to 1 minus y squared and lying between the vertical planes x plus y equal to 1 and x plus y equal to 3. Okay, so let's draw that. We have cylinder z equal to 1 minus x squared. So this cylinder is free with respect to the x, right? And we know that this cylinder should be perpendicular to the YZ plane, right? So I have the following picture. have z in here. This is y, this is the x. Okay, so this cylinder is y equal to 1 minus z equal to 1 minus x squared. I have to draw the parabola z equal to 1 minus y squared, right, on the yz plane. So basically, when z equal to 0, y is 1, and when y is 0, z is also 1 right here. So I have some, part of that parabola on the yz plane. Remember that we are considering the first arctan only. Okay, so since that is free with respect to the x, I have the following picture. Makes sense? So we have some cylinder like this. Okay, and then we need to draw two planes, x plus y equal to 1 and x plus y equal to 3. Actually, they are parallel, right? So I have to draw two straight lines, x plus y equal to 1. And since this is free with respect to the z, that is perpendicular to the xy plane. Okay, so it's pretty easy. X plus y equal to 1, I have like this. When y equal to 0, x is 1 and y1 is 0, x is 1, right? When x is 0, y is 1. So we have this straight line. That is the first one. Is x plus y equal to 1. Okay. For the guy x plus y equal to 3, I just shift this, right? Oh, sorry. I just shift this up to, to 2, right? So basically, in the xy plane, I have the following one. Let's say here is 1. Suppose that this is 3. Okay, so we don't have to go really far from that. I have another straight line. This is 3. So this is x plus y equal to 3. Makes sense? And this parallel, and of course they will intersect with our cylinder right here. So I make some cut in this. Agree? And for this guy I have some cut right here. So basically our solid region look like this. Okay, something like this with the cut in here. Okay, so with the cut in here, it looks like this. Sorry. So I have to erase this. I can erase this. Okay, and in here I have cut like this. Okay, I think I can erase this for you it is easier to see. So that is our solid region. They ask us to find the volume of this solid region. Make sense? All right, so again we need a triple integrons, right? This is our region. Don't forget that our region look like this. Okay, so the triple integron dv. Now you can decide to rewrite this integron, in the order dx, let's say dz, dy, dx, right? Whatever you want. But let's do both, right? We can write dz, dx, dy. All right, so for the first case, I have to find the integration limit with respect to the z, right? So for that, I will pick some point in the region xy, okay? So I can find the interval of z. So I need to make some, horizontal, some vertical line that will intersect with the surface at the point z equal to xy in here. Makes sense? So I have to find this point. Basically, from that observation, if we write in the first order, I will have the following integral. For the z goes from 0, right? Because this is 0, makes sense, the 0 right here, okay? And to the function value. The function value is z. Where's that? Z is equal to 1 minus y squared right here, okay? So I have 1 minus y squared dz. Now I fix x. Look at this, our region in the plane, right? So let's make that correctly, otherwise we cannot, you know, find the integration limits. So I have x in here, y in here. The first one is x plus y equal to 1. The next one is x plus y equal to 3. And we consider y just between 0 and 1, right? Y is between 0 and 1. Look at this. Y is only on this interval, 0 and 1. So we only have 0 and 1 right here. And this is, you know, our region. Makes sense? All right, now look at this. For this region, probably if you fix x, right? If you fix x, you might have complicated integrals, because, you know, we have 3 cases in here. The first case, when x is in between this, you have in this interval. The second case, when x is between this guy and this guy, right? So the last case, the third case is right here. So I think in this situation, this choice is not really wise. So we may choose the order dx dy, right? Why? Because for the x dy, you will fix y. But each time when you fix y, you have only one straight line right here. You see that? So you only need to find this point and this point. That's it. Make sense? So probably I will not write in the form dy dx. I choose the x dy. Okay. So if I fix y in here, I can find these 2 intersection points. So that is, you know, nothing but 1 minus x, and this is 3 minus x. Makes sense? And then my integral in here should be from 1 minus x to 3 minus x. Okay. And the next one should be, should be 1 minus y, 3 minus y, sorry, because we are looking for x, right? So and then the next one, once we fix y go from 0 to 1. So I have 0 to 1 right here. That's it. Make sense? I would like to challenge you to consider 3 cases in here, right? As I just mentioned, and rewrite this integral in the order dz, dy, dx. How about that for extra credit? Okay. So I think I finished my lecture right here. If you have any questions, just feel free to let me know. All right. Thank you.